Good day, people. I hope you are all well. Today we are going to speak about uh, continuous random variables. We are going now in a new topic. We are now unlocking a new topic, which is continuous random variables. Hence, we already unlocked a discrete random variable. So you need to recall what did I say? What did I say last time? I said there is a difference between a discrete and a random and a continuous. I mean, a discrete and a continuous. If we speak of discrete, it is something that is separable. So we speak of random variables, basically, like if you are counting fingers, something that is separable and countable. However, when you speak of a continuous, we are no longer speaking of separable, we are speaking of now inseparable. So we are now looking at similarities now, you see. Hence, you know very well that there is also a difference between a hypergeometric distribution and also the binomial random distribution. You know the similarities as well as differences. Then let us unlock the introduction. Here is the introduction. It says you need to remember that discrete random variables. Okay, before I proceed, you also need here to become familiar with experiments under each random distribution, which is a continuous random variable. Basically, you need to understand the experiment under each distribution, as we said last time on finite. You see, now we are no longer in finite sequences. However, now we are in finite sequences. You need to recall your metric, whereby you were told that the geometric sequence is differentiated into two. There is a finite and infinite geometric sequence. The one that consists of Sn, it's a finite. The one that consists of S infinite, it's an infinite geometric sequence. So now we are no longer looking at Sn. However, now we are on S infinite. So remember that discrete random variables can only take a countable number of possible values. This is very important, that discrete random variables can only take countable, you see, as I've already mentioned. Like fingers are countable: 1, 2, 3, 4. As I've already mentioned in the class, that you can't count water. However, you can measure water. You can use a measurement, you see. This is what we actually discussed. So remember that discrete random variables can only take countable, this is very important, number of possible values. Okay, we are looking at possible values, the possible outcomes, basically. So on the other hand, a continuous random variable has a range in the form of an interval or a union of an overlapping intervals on a real line, in bracket possible the whole real line. You see now what is happening. X now is not taking now a value. Hence, on discrete random, X was taking a countable number of possible outcomes, but now on continuous, X has now a range in a form of interval. Now, you see, when you speak of interval, you are basically referring to maybe 0 to 1, 1 to 2, numbers between 0 and 1. We are referring to intervals now, you see. So basically, on finite, we are not referring to intervals, we're referring to whole numbers, you see. We're referring to wholes. So let us proceed. Then what it says, a continuous random variable has a range. You know, when speak of range, the y values in the form of interval or a union of overlapping intervals on the real line. You see, now we need to integrate the union. When you speak of the union, what are we actually referring to? The union events. You know, the union events, they do not consist of an intersection, right? There is nothing common. These are disjoint sets, not a subset, to get my point. So let us go. Also, for any x elementary r, so it means the domain, basically. Probability x is equal to x, you know the story. is equal to 0, to get my point. Then thus we need to develop a new tools to deal with these continuous random variables. Okay, the good news is that, the fascinating news is that the theory of continuous random variable is completely analogous. So you see, if something is analogous, as I've already mentioned in class, that in our session, that when we speak of something that is analogous, there is an analog and analogy. You see, there is analog and analogy. So basically when you speak of analog and analogy, so if I nokuthi lento engangisho eclassini ukuthi if ngifuna, I want to present a topic about circuits, what I can use something that is similar to circuit. I can use a pipe, movement of water. You see, I can say a pipe represent a metal, a wire in a circuit, to get my point. So these are analog. These are analogs. When you speak of, there is an analog and analogy. So if I am going to represent a topic about circuit, so you know what is analog, what is analogy, to get my point. So basically, if we speak of an analog, you are taking something that is similar to what you are going to teach about, basically. So as I've already stated in class before, okay, then it says what I've already said before. Then let's continue. The good news, okay, then it says, when it continues, the good news of this theory of random variable is continue analogous, as I've already said, the theory of discrete random variable. You see, iyasho ukuthi continuous variables are completely analogous to the theory of discrete random variable, meaning they are analogous. There are some similarities between discrete and continuous. Hence, you know ukuthi in discrete we are speaking of finite, and on continuous we are no longer speaking of finite. However, we are referring to infinite. Then it continues. It continues, says, indeed, if we want to oversimplify things, we might say the following. Take any formula about discrete random variables. You see, you take the formula about discrete random variables because there are similarities. It is analogous. You see, that's why it is analogous. There are certain similarities. So it says take about the formula of the random variables and then substitute, replace sums with integrals, you see, and replace PMFs with probability density functions. You know, when you speak of a PMF, we are basically referring to a probability density function, because when you speak of MS, we are referring to a density basically, and you will get the corresponding formula for continuous random variable. That what it says, if something is corresponding, it means it's equal. You know, there's corresponding angles in Euclidean geometry. If angles are corresponding, they are equal. You are referring to those scenarios. Then of course there is a little bit more to the story, and that's why we require a chapter. We need a chapter to discuss it. You see, we need a chapter to discuss these certain events that are infinite, basically these continuous events. This is just an introduction. So it says in this chapter we will also introduce mixed variables that are mixtures of discrete and continuous. So now you are being alerted that in this chapter you are going to be taught about mixed random variables, which is a mixture of basically a discrete and a continuous. You need to first understand the discrete and understand the continuous, then able to mix them, both of them. So now when we are speaking of a mixed random variables, we are basically referring to a discrete random variable plus a continuous random variable. This is just an introduction. I will continue. Pause a video, then continue to in next page. Yeah.